My name is Philipp Schneider. I'm with the NILU, which is the Norwegian Institute for Air Research. And the topic I'm working on in hackAIR is actually one that is a little bit behind the scenes, but is important in the sense that it allows us to give users estimates of air quality anywhere, even if no locations are available. And what we call this is a data fusion approach to mapping in hackAIR. Now, I want to give you a short overview about what we do there at a very general level, and also want to start out now and showing you why we do this in the first place. So the motivation here is that in hackAIR, we collect many different point-based observations. So this includes, for example, image-based estimates like Lefteris just showed, but also we have these hackAIR Home, these open hardware sensors that people start to distribute. And many other sources of information from other projects and so on. And we use all these to basically get information about air quality. And all these sources have different accuracy levels, right? But what we need to do in the end is to provide the users of hackAIR with personalized air quality information at any location, even if there is no observations at that point available right now, and to visualize these observations. So essentially, we start out with something like this. This is, for example, for Germany, we have a set of observations. They are usually in terms of classes like low, medium, high air pollution, and so on. But what happens if we have a user right here which does not have access to an observation right here, but we still want to provide an estimate or personalized information? In order to do that, we need to basically use a technique that allows us to get something like this, that it provides air quality estimates all over our study site. And this is, of course, a simplified example, but in practice, we use a technique that we call data fusion. And this allows us to achieve spatially continuous maps using these techniques. And I'm not going to go into these mathematical details, but these are based on geostatistics and spatial interpolation using proxy information data set. But essentially what we do is we take the observations that we get from hackAIR over a domain, we average them over a certain time period, and then we combine those with the observations or the predictions from a model. Here on the right-hand side, you see the information from the CAMS, which is the Copernicus Atmosphere Monitoring Service. This provides up-to-date information on air quality, but it's not always accurate, right? And so, but what it does, it allows us to basically interpolate the observation that we get from hackAIR in an objective and meaningful way. And so if you combine these two data sets using data fusion, we get a fused map that basically inherits the spatial patterns of the model, but uses the magnitude of the observations from hackAIR, and basically gives us a continuous, spatially continuous map of air quality information using the hackAIR observations. Now, in terms of spatial scale, I want to mention that we are currently producing these at the country level. We're using this for both Germany and for Norway because these are our main study sites. These maps have a spatial resolution of 5 kilometers. So it's important to understand that we provide information about the regional air quality. So we can, for example, extract from these maps the air quality at the city level, right? We can say in Berlin, the air quality currently is such and such. What we do not provide with these maps is a street level estimate. So we cannot say at 10 meters from the house of a user, the air quality is high or low or whatever. But we will be working on this, and there has been some first experiments on this. These local urban air quality maps we are producing for Oslo when we have a dense enough network of these hackAIR Home units, the SDS-011s. Then we can do this, and then we can provide more spatially fine-grained estimates, and I will show a couple of slides at the end about this. But first, let's talk about the country-level estimates. Here's a map of, this is actually a long-term average map of the hackAIR data fusion maps. This is averaged over several months here, just to point out the typical spatial patterns that we see from these data fusion maps. For those of you that are familiar with Germany, you will see that, yes, you do see the strongest air pollution in the Ruhr area here in Western Germany, and the lowest air pollution in the very far north and the very far south. You also see some of the hotspots around the major cities, Hamburg, Berlin, Hanover. Interestingly, you do not see a hotspot in the Stuttgart area, which is always a hotspot for particulate matter. I'm not entirely sure. It could be related to the spatial scale that we use here, that these really localized air pollution problems that Stuttgart has do not show up in this type of map. But overall, we get very realistic spatial patterns for the long-term mean. The highest pollution levels are in the rural area over the long term, and we see the smaller hotspots. Now, I should also mention that what you see here in terms of spatial pattern, this is an air quality index, which I call the hackAIR air quality index. We use here an internal representation of 1 being very good, 2 being good, 3 neutral, 4 bad, and so on. What you already see here in this map, that over the long-term average, we are in very low levels. We are between very good and good. But this is because we're averaging over a long period. For individual hours, these values can range quite higher than this. Here are a few more examples. These are 3 consecutive days in February 2018, and you see nicely how the air pollution patterns shift from day to day. So for example, on the first days here, we have the strongest hotspot over the Berlin area, and in general over Eastern Germany. But then, for example, on the next day, the hotspot shifts to the southeast a little bit. And then 1 day later, the main hotspot is again in the Ruhr area, where sort of Berlin is much lower and the entire northern Germany is much lower as well. So you do see sort of these temporal patterns already in just individual daily maps. Here's the same thing for Norway, which is our other study site. Norway is a bit difficult site in the sense that overall at the country level, the air pollution is extremely low. Norway does have significant air pollution issues, but only in some cities and then only at a very localized level on the order of a few hundred meters or a few kilometers. So we cannot accurately predict this in these maps. However, we still do see some of the patterns. So what you see here in this map, for example, is the Oslo area and the entire Oslo fjord has the strongest air pollution here on this particular time period. And you also see hotspot over Bergen, Stavanger, Kristiansand, and Trondheim, and so on. But overall, the levels of pollution are quite low here. Here's an example of how these maps change over time. So each of these panels shows 1 hour estimate. But it's important to say that the maps are updated every hour, but they represent the average over the last averaging period, so the last 24 hours. So you see how they change over time, but they change slowly, of course, right? So this is hourly changes, but over about 3 or 4 day period. And you see how basically we have the hotspot in Berlin, which then slightly goes away, and then we have relatively low air pollution throughout the middle of the period, and then we increase in air pollution again towards the end of the period, and then have sort of the strongest hotspots here in Western Germany. So this is the kind of information that you can extract from this. Now, here's the same thing for Norway. Again, we have the hotspot over Oslo, which then goes away. We have lower pollution levels in the middle, and then stronger pollution again towards the end. So this is a temporal perspective. Another way to represent these temporal changes is to extract time series from our data fusion maps. And I did this here for multiple cities in Germany. And basically, each of these lines shows the temporal evolution of our hackAIR air quality index at this particular location, at this particular city. And here on the y-axis, you always see our classes from very good, good, medium, bad. And you can see that for most of the sites, the temporal the time series varies from very good to good, but we also have cases, for example, here Cologne or Düsseldorf in mid-January, where we go up into the bad range. So there are cases like this as well. If we compare with station data, we did this here for Oslo just to see how close we get to the official measurements. And what you see here in red is the averaged hackAIR air quality index over the sites here in Oslo, and in blue, the estimate from the data fusion index. And we get relatively close to it, but there are, of course, some cases, for example, here, where the data fusion either underestimates or for example, yeah, here also underestimates the official measurements. And so this could be related, for example, to individual sensors showing an outlier, or it could be related to other issues that we cannot currently foresee. But overall, the correspondence is relatively good, and we can also see that here in a scatter plot, where here on this axis we show the observed class of the hackAIR quality index, and on this axis we see the predicted, the data fusion class, and we see that overall we have a good correlation with a correlation coefficient of 0.72. We have some slight underestimation for higher values, but I think the sample size here is not good enough to really draw any strong conclusions on this. But overall, we are quite happy with how the data fusion performs compared to official measurements, especially considering the difference in spatial scales. Remember that we predict at a 5-kilometer grid raster, whereas these observations are made at stations which are representative maybe on the order of a few hundred meters at best. At the end, I want to talk about a little bit of an outlook, and that is the urban scale data fusion. So what you see here on this map is a map of Oslo, and the blue sides indicate some low-cost sensors that we distributed for a different project. This is not hackAIR, I should mention this, but we're hoping to get to the same level with hackAIR within this year. And the blue sides are the low-cost sensors, and then red, it shows the official monitoring stations. So you see how much more dense information we can get from low-cost sensors. And if we have a network like this one, then we can really start to produce urban scale air quality maps that can really provide street level estimates of pollution for individual users. Now, we want to try this for the SDS011 sensors, and we're hoping that we can get enough in Oslo. And when we do, then we can produce maps like this, which basically provide the air quality estimate at a very fine grain, where you see here in Oslo, the downtown area with the highest pollution. You see the highest pollution here along some of the major road links, the ring roads, some of the major freeways, and so on. So this is the kind of information that can be then really useful to the users, in the sense that we can predict the air quality close to their home. We can also extract air quality, for example, along bicycle lanes, to provide really a customized, personalized set of air quality information to the user. So this will happen this year. And in summary, the data fusion module has been running operationally now since mid-August 2017. As I said, it's a bit behind the scenes. It does not show by default on the hackAIR portal, but is being used in the background to provide personalized recommendations for any site that the user might be interested in. The module currently provides hourly updates for the average hacky for the last 24 hours. So we're thinking about maybe reducing this period in the future, but for now it's serving us well. The spatial patterns of the map look very realistic from in my opinion. The temporal patterns also look mostly as expected. And if you do a quantitative comparison, we see a good correspondence between the station observations and the data fusion maps, with a correlation coefficient of about 0.72. As I said, urban scale mapping experiments for Oslo are coming later this year. Thank you very much.